When I say that Mars lost its atmosphere, I'm really telling a story about gravity, energy, and time. I am also telling a story that connects a small, cold world in our solar system to the largest structures in the universe and even to dark matter and dark energy. At first, that might sound like a stretch. Mars is a rocky planet. Dark matter and dark energy shape the cosmos. But they are all part of one physical picture. To understand why Mars is the way it is today, I have to think about how matter clumps, how gravity works, how stars evolve, and how energy flows through space-time. I will start simple. Mars today has a very thin atmosphere. The surface pressure is less than 1% of Earth's. Liquid water is not stable on the surface for long. It either freezes or boils away. But we see strong evidence that in the past, Mars had rivers, lakes, maybe even long-lived seas. We see dried river valleys, deltas, sedimentary layers, minerals that form in liquid water. That means the ancient Martian atmosphere must have been thicker and warmer. The central question is, where did that thicker atmosphere go, and why did Mars not hold on to it? One of the first things I think about is gravity. Atmospheres are held by gravity. The stronger the surface gravity, the easier it is for a planet to hold on to light gases, especially over billions of years. Gravity itself is not a force that travels through space as a push or a pull in the modern view. In general relativity, gravity is the curvature of space-time caused by mass and energy. A planet like Mars is a local dent in the fabric of space-time. Gas molecules follow paths in this curved space-time. If they move too fast, they can climb out of the gravitational well and escape to space. Mars has about 38% of Earth's surface gravity. That difference matters. The average speed of gas molecules depends on temperature and molecular mass. For a given temperature, lighter molecules move faster. Hydrogen and helium are the easiest to lose. Heavier molecules like carbon dioxide are harder to lose. But if a planet is small and cold and exposed to energetic radiation, even heavier molecules can be stripped away or broken apart, and their fragments can escape. Over billions of years, this slow leak adds up. The escape of gas is not just simple thermal escape. There are multiple processes. Thermal escape, or Jeans escape, is when the high-speed tail of the Maxwell-Boltzmann distribution lets some molecules exceed escape velocity. There is also non-thermal escape. Charged particles from the solar wind can transfer energy to atmospheric particles. Ultraviolet and X-ray photons from the sun can ionize and heat the upper atmosphere. This can drive atmospheric sputtering, ion pickup, and other processes that remove gas. To see why Mars is so vulnerable, I have to compare it to Earth and to Venus. All three are inner rocky planets. They formed from the same protoplanetary disk. That disk itself was a small piece of a giant molecular cloud that collapsed under its own gravity. That collapse was not random. It was guided by the underlying gravitational potential of the Milky Way, which is dominated by dark matter. Dark matter does not interact with light, but it does curve space-time. It provides most of the gravitational glue of our galaxy. Without that dark matter halo, the gas that formed the sun and the planets might not have collapsed into a stable rotating disk at all. So the very existence of Mars as a planet is already a consequence of how matter, including dark matter, is arranged in space-time. Inside that disk, dust grains stuck together, forming planetesimals, then protoplanets. Their growth depended on local density, collision history, and orbital dynamics. Mars ended up smaller than Earth. One leading idea is that Jupiter's early migration disrupted the material in the region where Mars formed, limiting its growth. Whatever the detailed cause, Mars ended up with about 1/10 the mass of Earth. That means a shallower gravitational well, less ability to hold onto a thick atmosphere over cosmic time. But mass alone is not the whole story. Earth has another key defense: a strong global magnetic field. Our liquid iron outer core convects and rotates, generating a dynamo. That dynamo produces a magnetosphere that deflects most of the solar wind. The solar wind is a stream of charged particles flowing outward from the sun. It is tied to the sun's magnetic field and carries energy and momentum. If the solar wind hits an unprotected atmosphere, it can gradually erode it, especially when the sun was younger and more active. We think Mars once had a magnetic field early in its history. Evidence from ancient crustal rocks shows remnant magnetization suggesting that Mars had a dynamo that later shut down. The most likely reason is that Mars cooled faster than Earth. A smaller planet loses internal heat more quickly. Once the core cools and solidifies enough, convection slows or stops, and the dynamo weakens or dies. When that happened on Mars, its global magnetic shield faded. The solar wind could then interact directly with the upper atmosphere. This is not just a theoretical picture. We have measurements. NASA's MAVEN mission, the Mars Atmosphere and Volatile Evolution spacecraft, has been orbiting Mars since 2014. Its job is to measure how the solar wind and solar radiation interact with the Martian atmosphere. MAVEN has seen atmospheric ions being picked up by the solar wind and carried away along magnetic field lines. It has measured escape rates for oxygen, carbon, and hydrogen. By combining these rates with models of the sun's past activity, scientists estimate how much atmosphere Mars has lost over billions of years. The evidence points to a large loss. Isotopic ratios in the Martian atmosphere, measured by missions like Curiosity and others, show enrichment in heavier isotopes. For example, the ratio of heavy to light isotopes of argon and hydrogen is higher than we would expect if no escape had occurred. Lighter isotopes escape more easily. Over time, the atmosphere becomes isotopically heavy. This is like a fingerprint of atmospheric loss. It tells us that Mars once had more gas and more water than it does now. So one key reason Mars lost much of its atmosphere is that it is small, cooled fast, lost its dynamo, and then its unprotected atmosphere was slowly stripped by the solar wind and heated away by solar radiation. But I can go deeper because this is also a story about energy flow in space-time. The sun is a middle-aged star. It shines because nuclear fusion in its core converts mass into energy. That energy eventually escapes as photons and as kinetic energy in the solar wind. Those photons and particles move through space-time, following null and time-like geodesics shaped by the sun's mass and by the overall curvature of the solar system. When those photons reach Mars, some are absorbed in the atmosphere and at the surface. That energy heats the gas. Heated gas expands, rises, and in the upper atmosphere, some molecules can reach escape velocity. High-energy ultraviolet photons can dissociate molecules like CO2 and H2O. They can ionize atoms. These processes change the composition and structure of the atmosphere. The balance between energy input from the sun and energy lost to space sets the thermal structure of the atmosphere. For Mars, that balance has changed over time as the sun brightened and as Mars' atmosphere thinned. The sun itself did not form in isolation. It formed in a galaxy whose large-scale structure is shaped by dark matter. On even larger scales, the expansion of the universe, driven today by dark energy, sets the overall context for how galaxies evolve and how long stars can shine. Dark energy is the name we give to the observed accelerated expansion of the universe. In general relativity, we describe it as a component with negative pressure or as a cosmological constant term in Einstein's equations. It acts uniformly, stretching space-time on the largest scales. On the scale of the solar system, dark energy's effect is tiny. It does not directly strip Mars's atmosphere, but it does influence the long-term fate of galaxies, of stars, and of planetary systems. If the universe were not expanding the way it does, the history of star formation would be different. The rate at which gas cools and collapses into galaxies depends on the competition between gravity, which pulls matter together, and expansion, which pulls it apart on large scales. Dark matter enhances gravity locally. Dark energy accelerates expansion globally. Their interplay determines when galaxies like the Milky Way form, when stars like the Sun are born, and how long the cosmic environment remains friendly to planet formation. Mars is a product of that cosmic timeline. Its atmosphere was built and lost within that larger space-time story. On smaller scales, gravity also controls how atmospheres behave. The escape velocity at the top of Mars's atmosphere is lower than on Earth. Escape velocity is given by the square root of 2gmr, where g is the gravitational constant, m is the planet's mass, and r is its radius. This comes directly from energy conservation in a Newtonian approximation, which is a good description at planetary scales. Molecules in the upper atmosphere have a distribution of speeds. The fraction that exceeds escape velocity depends on temperature and molecular mass. For Mars, that fraction is larger than for Earth, especially for light gases and under strong solar heating. There is another important factor. Mars receives less sunlight than Earth because it is farther from the sun. That might suggest it should be colder and hold onto its atmosphere more easily. But a thinner atmosphere traps less heat. Greenhouse gases like CO2 and water vapor can warm a planet by absorbing infrared radiation. Early Mars may have had a thicker CO2 atmosphere, providing a stronger greenhouse effect. As that atmosphere was lost, the greenhouse effect weakened, the surface cooled. Water froze or sublimated. Colder temperatures reduce some escape processes, but also reduce outgassing from the interior. Volcanic activity can replenish an atmosphere. If volcanism declines as the planet cools, the supply of new gas drops. For Mars, the balance shifted toward net loss. We know Mars had large volcanoes. Olympus Mons is the tallest known volcano in the solar system. That tells us Mars was once geologically active. Volcanic outgassing would have released CO2, water vapor, sulfur compounds, and other gases. Over time, as the interior cooled, volcanic activity decreased. Without a strong internal heat engine, both the dynamo and the volcanic outgassing faded. The atmosphere then became a one-way system. Lost to space and to surface reservoirs like polar caps and minerals exceeded any new supply. Scientists test these ideas with multiple lines of evidence. We use spacecraft measurements of present-day escape rates. We analyze Martian meteorites that have landed on Earth, which preserve isotopic and chemical clues about ancient conditions. We compare crater counts on different surfaces to estimate ages of geological features. We use climate and escape models that solve equations for radiative transfer, chemistry, and fluid dynamics in a Martian context. We also use comparative planetology. We look at Venus, which is similar in size to Earth but has a very thick, hot atmosphere, and at Earth itself, which maintains a moderate, stable atmosphere. The differences help us identify the key factors: mass, distance from the sun, magnetic field, geological activity, and initial volatile inventory. There are still uncertainties. We do not know exactly how thick the early Martian atmosphere was or for how long liquid water was stable on the surface. We do not know the exact timeline of dynamo shutdown. We have estimates, but not precise dates. We do not know how much of the water was lost to space versus locked into the crust as hydrated minerals or ice. MAVEN and other missions are narrowing these ranges, but the picture is not complete. This is where I connect back to gravity and space-time in a deeper way. General relativity tells me that mass and energy curve space-time, and that curvature tells matter how to move. Planets orbit the sun along geodesics in this curved space-time. Atmospheres are thin layers of gas bound in local gravitational wells. On the scale of the solar system, I can often use Newtonian gravity with small corrections. But the underlying theory is still general relativity. When I calculate escape velocities, orbital energies, or the stability of planetary orbits over billions of years, I am working within a space-time shaped by the sun's mass, the planet's masses, and the background cosmology. Dark matter's gravitational influence is mainly felt on galactic and larger scales. It shapes the Milky Way's rotation curve and gravitational potential. That potential affects the Sun's orbit around the galactic center. Over hundreds of millions of years, the solar system moves through different parts of the galactic environment. The density of interstellar gas and the rate of nearby supernovae can vary. In principle, these changes can influence cosmic ray flux at Mars and Earth. Cosmic rays can affect atmospheric chemistry and, at high energies, contribute to atmospheric escape. These effects are subtle compared to the dominant role of the Sun, but they show how planetary atmospheres are not perfectly isolated. They exist in a layered gravitational and radiation environment shaped by both visible and dark matter. Dark energy enters when I think about the ultimate fate of planets and their atmospheres. In a universe with accelerated expansion, distant galaxies recede faster and faster. On local scales, gravitationally bound systems like the solar system are not being stretched apart by dark energy in any noticeable way. But dark energy does set the long-term horizon for structure formation. Over trillions of years, star formation will decline as gas is used up, and as expanding space makes it harder for new structures to form. Stars like the Sun will eventually exhaust their nuclear fuel and evolve into red giants and then white dwarfs. Long before that, the Sun will brighten enough to strongly affect the inner planets. In about 1 billion years or so, the Sun's increasing luminosity will likely make Earth's surface uninhabitable. For Mars, the story is different but related. As the Sun brightens and later swells into a red giant, Mars' surface environment will change dramatically. Its thin atmosphere may thicken slightly if ices sublimate, but intense solar radiation and stellar winds in the red giant phase will strip away what remains. In the very long run, no rocky planet in the inner solar system will keep a thick atmosphere. The fate of Mars's atmosphere is part of a general trend. Planetary atmospheres are temporary features in a universe where energy flows from hot stars into cold space. This connects back to entropy. As the universe expands and ages, energy becomes more evenly spread out. Structures like stars and planets are local pockets of low entropy that form because gravity pulls matter together. But over very long timescales, even these structures will evolve toward higher entropy states. Atmospheres leak, stars die, galaxies fade. Dark energy accelerates the separation of distant structures. But inside bound systems, gravity still dominates. Mars losing its atmosphere is a small step in this larger thermodynamic and gravitational evolution. When scientists say we know that Mars lost much of its atmosphere to space, we mean that multiple independent observations and well-tested physical theories point in the same direction. We have direct measurements of escape processes today. We have isotopic evidence of past loss. We have theoretical models of solar evolution and atmospheric physics. We have comparative data from other planets and moons, like Titan, which retains a thick atmosphere thanks to its low temperature and different environment, and like Mercury, which has almost no atmosphere and sits very close to the Sun. All of this builds a coherent story, but we also recognize what we do not know. We do not know the exact initial conditions of Mars' atmosphere. We do not know all the details of how early impacts, including large asteroid or comet collisions, may have added or removed atmosphere. A giant impact can blow off part of an atmosphere, especially on a small world. Did Mars experience such events at key times? We have some evidence of large impact basins, but linking them to specific atmospheric changes is hard. We also do not fully understand the coupling between Mars' interior, crust, and atmosphere over time. How much CO2 is locked in carbonate rocks beneath the surface? How much water is trapped as ice kilometers down, or chemically bound in minerals? Future missions that can drill deeper or bring back more samples will help answer these questions. They will give us tighter constraints on the total volatile inventory of Mars and how it has been partitioned between atmosphere, surface, and interior. On the cosmological side, we still do not know what dark matter and dark energy actually are at a fundamental level. We infer dark matter from its gravitational effects, galaxy rotation curves, gravitational lensing, the cosmic microwave background, large-scale structure. We infer dark energy from the accelerated expansion measured with distant supernovae, the CMB, and baryon acoustic oscillations. These components dominate the energy budget of the universe. They set the stage on which galaxies and stars form. Yet we do not know their particle nature, or whether dark energy is truly a cosmological constant or something that changes over time. If dark energy evolves, the long-term fate of the universe could be different. That would change the ultimate context for planetary systems, though not the specific history of Mars over the last few billion years. If dark matter has complex interactions beyond gravity, that could in principle affect galaxy evolution in more subtle ways, which then feed down into star and planet formation histories. Right now, the standard cosmological model, lambda CDM, works very well at large scales. It tells us that the universe will keep expanding, galaxies will drift apart, and over enormous timescales, structures will thin out. Mars's lost atmosphere is a small story within that larger narrative, but it is consistent with it. Returning to Mars itself, I can summarize the key physical reasons for its atmospheric loss in simple terms. Mars is small. Its gravity is weak compared to Earth's. It cooled quickly. Its core stopped generating a global magnetic field. Without that shield, the solar wind and high-energy radiation had direct access to its upper atmosphere. Over billions of years, these processes stripped away much of its original air and water. Volcanic outgassing slowed, so the atmosphere was not replenished. The greenhouse effect weakened. The surface cooled and dried. The Mars we see today is the result. Yet some details remain open. One of the most important unresolved questions is this: exactly how much water and atmosphere did early Mars have? And for how long did it maintain conditions that could support stable liquid water at the surface? We've evidence for ancient rivers and lakes, but we do not yet have a complete quantitative timeline of atmospheric pressure, composition, and loss rates over the first billion years. Pinning down that history is an active area of research, and it will tell us not only why Mars lost its atmosphere, but also whether it ever had enough time and stability for life to emerge before that atmosphere was gone.